Hello teammates, it's Mr. Nanini coming to you from the physics bunker. It's been a long day here in the bunker. And I lost my light. It's dark outside. But I hope this works. We're gonna sharpen up the prudent pencil of physics. And Luna's gonna visit us early. If you haven't watched the video from Flipping Physics yet, please do that first and then return to this. We're on page 163, number 1. I'm going to take you through A, B, C, and actually A, B, and C. And I'm going to ask you to do D, E, and F and post that. And Luna's already visiting us. You want to say hi, Luna? Yeah. Thanks. So let's go. First, how much would a 1,500 kilogram satellite weigh near the surface of the moon? So let's step back. And like Mr. Thomas Palmer did, we know that force gravity is m times g. Yeah. And we know that the mass of our satellite, is 1,500 kilograms. And if we're on Earth, we use 10 meters second, or 10 newtons per kilogram for that conversion to go from mass to weight. The moon's gravitational strength, though, is 1.6 newtons per kilogram, or 1.6 meters second. Cat, go. It is late. 1.6 newtons. And so the weight, you're just a little pest. The weight of the satellite on the surface of the moon would be 2,400 newtons. So while your mass doesn't change, your force sure does. Your weight does. So your mass is the same no matter where in the universe you are. But your weight changes. That's why if you see those videos of the astronauts bounding across the surface of the moon, their mass is still the same, but their weight is less. So it takes less force for them to move. And there you go. So just to compare, on Earth, the weight would be 15,000 newtons. On Earth. Come here. I gotta teach kids. Go somewhere. She's so happy. I don't know why she's so happy. It's good. Satellite is to have an altitude 100 kilometers above the moon's surface. What's the radius of the orbit? So that's going to visit what we did last week and what you saw in the Poco Fiesta. And I plant the seed, and then I come back and harvest it. So there's the moon. Here's the satellite. So the radius is going to be that R we're going to use is the radius of the moon plus the altitude of the satellite. So the radius of the moon, yes, 1.74 times 10 to the 6 meters. And the satellite's going to be at orbit 100 kilometers above the surface of the moon. Kid, you gotta go. And so that's going to be 100,000 meters, right? We never use kilometers. So we're going to add those two together, and that's going to be the radius, and that's how we're going to do these problems. If you're given the radius of a planet and some altitude away from the planet, or some height away from the planet, you're going to add those two together. And for this one, we're going to get 1.84 times 10 to the 6th meters. For that one. That's what we're going to use for our R. It's good. So let's look. Let me do this next one. So Mr. Thomas Palmer took you through a calculation for this. Let me walk you through how this looks. So this is going to be our first go with Newton's universal law of gravitation. So Sir Isaac Newton came upon this during the plague in the 1600s. He was attending university in Cambridge in England. They closed the university. We can all relate to that. And he went home to his family farm. People didn't know what it was that made the moon go around the earth. It was a great puzzle. And he reasoned it out. So we start with, so if the satellite's going around the moon like that, it's a centripetal force problem, isn't it? And so we want to calculate that force of gravity. In this case, that's going to give us a centripetal force. So Fg, also, and like Mr. Thomas Palmer said, and you saw in my puzzle, you can use Fg equals mg if you're near the surface, on the surface. If you're some distance away, you got to come to the universal law of gravitation. Big G, mass of object 1, mass of object 2, divided by the radius. And so your gravitational, your constant is right there. It's a really small number. But what's fascinating about that, and what makes this whole life of ours so miraculous, if Big G was just a little bit bigger, we would all have been smashed. The Big Bang would have happened, and everything would have smashed right back. The force of gravity would have been too great, and everything smashed right back. We wouldn't be having this conversation. If Big G was just a little bit smaller, things wouldn't hold together. Things would be scattered across the universe. Planets probably wouldn't have formed. Stars probably wouldn't have formed. So it's really quite remarkable, and the way this universe appears to be fine-tuned for us. It's very interesting. So let's calculate this. 6.67 times 10 to the minus 11th Newton meters squared, kilograms squared. I'm going to explain why that is in just a moment. Times our two masses. Mass is always in kilograms. 7.36 times 10 to the 22nd kilograms times 1,500 kilograms all over your radius that you calculated. You determined it. 1.84 times 10 to the 6th meters squared. So with your calculator, I want you to get some experience doing this, and I'm going to show you a technique. Well, first, let me show you how those units cancel. So meters, this number squared, meters squared is going to give you meters squared. Meters squared is going to cancel. Kilograms times kilograms, kilograms squared, that's a kilogram squared. Kilograms are going to cancel, leave you with newtons, leave you with force. Now here's what I recommend you do when you calculate this. I'm going to put this up here. All right, so when you calculate, here's what I recommend you do. So 6.67, use your exponent button. I don't recommend you do like 10 to the times 10 to the minus 11th. Use your exponent button. Negative 11. I always hit equal next. Times 7.36. Exponent button. 22. Times 1500. It's good to go. Equals. So far, so good. Now you're going to deal with this. Here's what you don't want to do. You don't want to do divided by this number and then square it, because it's going to take this top number, divide it by that number, and square the whole thing. You want the radius squared. So here's what I recommend you do. Divided by 1 point, let me put a parentheses, put another parentheses, 1.84 exponent to the 6th, parentheses, square that after the parentheses, close parentheses, equals, and you get 2175 newtons. And that's exactly what we want. 2175 newtons. So try that. We'll get some practice. It'll take some getting used to. But again, multiply, multiply, multiply. When you divide, it's this number squared. If you do this, if you go multiply, 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 divide by squared, you're not getting this number squared. You're getting this number divided by that number, square the whole thing. It's all right? All right, teammates. I'll put this on the assignment. I want you to take a shot at easy money at D, E, and F. Write that on a sheet of paper, take a photo, and post it to Schoology. Thanks for your patience, teammates. Luna she's been sitting here watching me. She is just very interested in universal gravitation, apparently. It's good. Let's see if we get a picture of Luna. You want to get in a picture? Luna. Luna. There you go. There's the Luna. All right, teammates. We'll see you later.